Well, you have seen this distribution before on a previous slide. It is called the continuous uniform distribution, and it has this form. So whenever you see a probability density function that has the form 1 over b minus a, and then x is allowed to be between a and b, then you have something called the continuous uniform distribution. Remember, we could also put equal signs here, or we could go less than or equal to, or we could go less than or equal to or less than, because the probability that x, which is clearly a continuous distribution, the probability equals anything is equal to 0. So if we apply the formula to get the expected value or the mean of x, it turns out that it works out to this very nice little formula called a plus b over 2. Same thing for the variance. If I apply the formula, the expected value of x squared minus the mean squared, I'm going to get b minus a squared over 12. And if I take the square root of that, I'm going to get the standard deviation. Now, to get the CDF of x, what we're going to do is, we go from, well, first of all, it's going to be 0 whenever x is less than a. And remember what capital F of x is. Capital F of x is the probability that my random variable is less than or equal to x. And for a continuous random variable, it could be just strictly less than x. So whenever x is less than a, I don't have any probability there. So the probability x is less than anything less than a has to be 0. We also know that it will equal 1 whenever x is bigger than b or bigger than or equal to b, because if I were to put my lawnmower right here and then I were to mow to the left, and that would pick up all of the probability that x is for any x bigger than b, make it b plus 1, I'm going to pick up all this probability, because we know that this area is equal to 1, because we also know that if we integrate over all of x of our PDF, that we get 1. So how do we get this? What is the function here whenever x is between a and b? Well, we're going to just apply that formula, which we've seen on previous slides. If I want to get the CDF of x, and it's a continuous random variable, I'm going to go from my low value of x up to some general value of x under the PDF of x. So that's what I'm going to do here. So if I start with the lowest value of x, which is a, and I go up to some general value of x over 1 over b minus a dx, I promise you, you're going to get x minus a over b minus a. So this is really nice, because then we can just use this formula for the CDF of x when we want to determine probabilities. We don't have to keep doing integrations and worrying about if our calculus is right. So here's an example of the continuous uniform. And again, it should look sort of familiar because we did something similar to it earlier on in the chapter. So suppose we have this PDF for the current in a wire measured in milliamps. And it says that the random variable is the current in a wire. It has a continuous uniform PDF, and that is over 4.9 milliamps to 5.1 milliamps. It says show the PDF, and what I mean by that is to show the equations for it. So we can see that A is going to be 4.9. You might be able to hear my little neighbor boy playing outside. He's very happy, and he's terribly cute. So you might be hearing him. And so this, if it's because they said specifically it's continuous uniform, we know that this is going to be 1 over b minus a. And that's going to be 1 over 0.2, which actually works out to be 5. And then it says graph the PDF of x. So I'm going to do that over here. So here is the PDF of x. And for any value between 4.99 and 5.1, the height of this is going to be 5. So a graph of it is going to be this rectangle like this. Sorry, I have an uneven table surface under here, so it's not beautiful. And we can see that this would obviously have the area of 1, right? This is going to be 5.1 minus 4.9, which is 0.2 times 5 is 1. So that's no surprise. So that's part B. Part C says determine the probability that a measurement of current is between 4.95 and 5.1. 0 milliamps. So I'm going to redraw this again. And what they want me to find is they're saying find the probability that my wire current, which again, the definition of X has been defined up here. X is the current in a wire. So what's the probability that the current in a wire is between 4.95 milliamps and 5.0, whoops, milliamps, sorry. And I could show a picture of that. It's just going to be this this strip of probability. If I were to do right here, 4.95, then what they want to know is what is the area, which is really just base times height right here. So that's going to be, it's just going to be 0.25, right? Because the distance here is going to be 0.05 times the height, which is 5. So we can see that that would just be 0.25. Another way to do C, though, if you wanted to, remember that, so I want to show this, another way to do part C. Remember what the CDF is. We could say that the CDF is 0 whenever X is less than 4.9 milliamps. And it's equal to X minus A over B minus A, which was that 5.1 minus 4.9. And that's good for X between 4.9 and 5.1. Well, if you do the algebra here, you're going to find that there's a nice, neat, easy way of, to write this, which is 5x minus 24.5, because the bottom is 0.2, and then I can do a little bit of algebra here. And that's going to be good for 4.9 milliamps less than X. Whoops, that should be a little X. Less than 5.1 milliamps. So that's my CDF. We know here that it's 1 whenever X is bigger than 5.1 milliamps. And anyway, to do C here, what I'm getting to a kind of in a long way here is I could just express this if I wanted to. I could say, well, the probability that X is between this 4.95 and 5 is just the probability that X is less than 5 minus the probability that X is less than 4.95. And each one of those is just the CDF here. So I could say this is just capital F of 5 minus capital F of 4.95. And then I can plug and chug into that equation there. So I can say, okay, this is 5 times 5 minus 24.5 minus 5 times 4.95 minus 24.5, and that will end up being 0.25. So again, why does this work? Well, if I highlight the probability X is less than 5, that would be this yellow area. And if I highlight the probability that X is less than 4.95, that's going to be this area here. And so when I subtract the blue area from the yellow area, I get the original shaded area, which is that 0.25. Part D says, show and graph the CDF of X. Well, that's convenient because we just developed it here. So pretty easy to do. Here is X. So this is going to be part D, this graph here. This is going to be the CDF of X. And we can see that it's going to be 0 until we get to 4.9 right here. Let me get a good contrasting, nice contrasting color here. So it's going to be 0 until we get to 4.9. And then when we get to 4.9, we're going to have the equation of a line. I hope you can recognize this. This is the equation of a line. It has a slope equal to 5 and an intercept at what we would say is negative 24.5. And that means it would be down here. But really, the easiest way to do this is we know this is a line. We also know that it's 1 when we get up to 5.1, right? So if it's got to be 1 by the time we get up to 5.1 and it stays there, then this is just a straight line between these two. I don't have to worry about rise over the run and anything. I just know that it's a straight line between 4.9 and 5.1 up to 1. And then I can plot it there. So I hope that gives you some good insight into the continuous uniform distribution.